Alright, so in this video we're going to deduce the formula for the arc length of a curve given in parametric form. So let's say that you have this curve that you have the parametric equations for, and you want to compute the length of this. So what you would do, again, as always, by the way, my starting point is x of a and x of b. A and b are going to be my endpoints for the time. And I'm going to partition this into subintervals as we normally do. And what we're going to do is we're going to approximate the length with the length of each one of these segments. So if you were to zoom into one of them, let's say you have this length right here, what would your length be here? Well, you will have to get two quantities. This one right here, which is going to be your y given at any time, so let's call it at time I, minus y at time I minus 1. I'm not going to be able to fit it there maybe. So it's going to be your delta y, if you will. And now here on this other side, you're going to have your delta x. So it's going to be your xti minus xti minus 1. Let me erase. I'm zooming into this. I don't need to make this so big. So let me erase so we can have room to write. All right. So this distance right here would be just x at ti minus x at ti minus 1. Alright, so this length here, and we can call this delta xi, and we can call this delta yi. So this length right here, let's call it L sub I. That L sub I is just going to be the square root of the delta xi squared plus delta yi squared. And so my goal now will be to add all these li's. The way I'm going to do it is I'm going to say that the length, so L, is going to be the limit as n goes to infinity of the sum from I equals 1 to n. So I'm going to have n partitions, and I'm going to take the limit as n goes to infinity, and I'm going to be adding these li's. So I'm grabbing each one of these lengths, adding them up. That's going to give me the total length of the curve as I take the limit as n goes to infinity. So I get a very precise, or I get the exact sum. All right, so that's going to just be the limit as n goes to infinity of the sum of from I equals 1 to n of the square root of delta xi squared plus delta yi squared. And this still is not good enough for us because we really cannot integrate, because my goal, by the way, last video I did remember, what I would want it to be is my integral from a to b and something that depends on dt. And I don't have that form right here, so I'm going to have to force that. So I have a delta x, so what I can do is divide by a delta t, a delta ti, which would be ti minus 1, and I'm going to multiply and divide by that to make it look the way I need it. Alright, so as I said, I'm going to go ahead and write this as the limit as n goes to infinity, and I'm going to have the sum from I equals 1 to infinity of, and I'm going to go ahead and write this as delta xi squared plus delta yi squared. Actually, I'm going to do an intermediate step. I'm going to multiply and divide by delta ti over delta ti. And then I'm going to introduce this delta ti in here, but I have a square root, so I have to square it, and I'm going to distribute it. So I'm going to do it in two things in one step. But that's just because I'm running out of space and I don't want to really run out of space. And so when I move this one in, I'm going to have to move it with a square. So it's going to be delta xi over delta ti squared plus delta yi over delta ti squared. And I'm going to have a delta ti out here. And here I have to be a little bit mindful because these are differences. And so this is going to be, each one of these delta xi over delta ti is going to be the slope of the secant line between each one of these points. And so I have to use the mean value theorem to know that there's going to be some value, say ti tilde, and then some value ti hat, for which this secant is going to be equal to x prime at ti tilde, and this one will be equal to y prime at ti hat. As I take the limit as n goes to infinity, this becomes dt. This one will just be x prime of t squared, and this is going to be y prime of t squared. And the formula that I obtain, I'm going to write it up here because I'm going to need it. I'm going to erase this, I'm going to write it up here, and I'm going to keep it here for the rest of the video almost. So we're going to go ahead and erase that, and I'll come right back. Alright, so continuing with my limit here. As I told you, then the arc length is going to be given by the integral from a to b, because my initial point in time was a and my end point in time was b. And then I'm going to have that square root of x prime of t squared plus y prime of t squared dt. And that is going to be my formula to use. Alright, so as an example, for if I give you a curve, let's say x of t is going to be e to the t cosine of t, for example, and then y of t is going to be e to the t sine of t. I'm using this one because I know it actually works quite nice with the integral. Remember, when you do arc length, sometimes these integrals are not as nice. Let's do time from 0 to pi over 2, for example. And let's see what that integral will look like. So at this point, it's just using your formula. So you're going to compute your derivative. Remember, there's a product, so it's going to be product rule. So you take the derivative of the first, just e to the t, copy the second, plus copy the first, derivative of the second, which is negative sign. So I'm going to smudge this here, but it's going to be negative sign. And then I'm going to have to square it. So let's go ahead and square it. So I'm going to take a common factor e to the t. So it's going to be e to the 2t because I'm going to square it. And then I'm going to have the square of cosine minus sine. Alright, and then we'll FOIL this out in a minute. Now we're going to do also y prime. And that is going to be, again, the same, a product rule. So it's going to be e to the t, derivative of the first, times the second, sine of t. This is going to be plus, copy the first, derivative of the second is cosine. And then you see that these are very similar. So the y prime of t squared is going to be e to the 2t. And then I'm going to have to FOIL the cosine of t plus sine of t squared. Alright, so now I'm going to erase this part. I'm going to continue with my calculation. I just have to plug everything in. I'm probably going to address this sum separately, and then I'm going to plug it into the integral just to make things simple, or simpler, I suppose. Alright, so I'm going to erase it and I'm going to be right back. Alright, so I decided against foiling all this out and doing all the algebra because the video is going to get too long, and that's just algebra. So please pause it. And when you square these things out, you're going to end up with cosine squared plus sine squared 2 times. So you're going to end up with a 2. and then you're going to have minus 2 times cosine sine plus 2 times cosine sine. Those will cancel out when you add them, and you're going to end up with that. So it's going to simplify very nicely. So your integral then becomes, so that's why I chose those two functions, because they're actually quite nice. So I really needed the pi over 2. It really didn't matter what I chose, and that's going to be the square root of this term that we computed. Well, I computed, you verified, to be this. So that's going to become just square root of 2. You can pull that out. Integral from 0 to pi over 2 of e to the t, because this e to the 2t, when you raise it to the power of 1/2, this is just e to the t squared. And so when you take the square root, you're going to end up with e to the t dt. And then e to the t remains the same. And so this one is going to be an ugly number. Well, not so ugly, but it's just e to pi over 2 minus 1. Remember, when you have exponentials or cosines, when you evaluate at 0, they don't cancel. That's a very typical issue, right? Because when you evaluate at 0, it's a 1. And so that's going to do that one. That's going to be it. Now, there are going to be several problems where you're not going to be able to compute the exact integral. So you have to do a numerical approximation. So expect that for this section, just because the integrals, I mean, I chose one that is just beautiful, but they don't always work that way. And so I'm going to now use this formula. I'm going to erase all this, and I'm going to show you how you do it when you have a function, but now in polar coordinates. So I'm going to erase, and I'm going to be right back.